Yes, this is 300 plus academy where all we do is exams, tutoring. We quickly look at heat curve and cooling curve, as well as use this heat curve as criteria for purity of a substance. So let us assume that we have ice, which is a solid at minus 20 degrees Celsius, and then suddenly we begin to heat. We begin to add heat to the ice such that the temperature begins to rise, such that the particles absorb the heat, and now they are able to vibrate more vigorously, so that the temperature suddenly moves from minus 20 to about minus 10 degrees Celsius, and then till a point is reached that's at zero. At this point, this is called the melting point. What happens at this point? Look at, as you can see here, AB, what we have for this material are all solid. In this case, we are using ice as example, and then at B, melting starts. Now, at this point, if we continue to apply it, we need to know that the heat is not going to manifest as an increase in temperature. It's not going to show as an increase in temperature. Reason why we talk about latent heat, hidden heat, because at this point, what this heat will do is to break the bonds between solid particles, so that solid now begins to change to liquid. This is why we talk of latent heat of fusion, hidden heat of fusion, because what will happen here is a change of state, and at that point temperature does not rise, temperature remains constant. Also, it is worthy to know that at this point, between B and C, we say solid and liquid are at equilibrium. That is to tell you that if I continue to heat my solid and I get to the melting point temperature, where the temperature does not rise again, but this part of the curve just flattens out. You need to understand all of the solid will not suddenly change to liquid. We have some of those solid particles that had acquired enough energy changing to liquid, leaving behind those solid that had not acquired enough energy. That's why we say solid and liquid are at equilibrium for the B and C portion of the curve. At point C, at point C, all of the solid must have completely changed to liquid. We say melting ends. And then at C and D, if we continue to increase the temperature, if we continue to add heat, the temperature continues to increase. You can see that CD tells me that all that I have here is liquid. So I continue to add heat, the temperature continues to rise until it get, or for water continues to rise until it gets to 100 degrees Celsius, whereby if I add more heat now, it is not going to result in an increase in temperature, but rather the curve again flattens out, telling me that a change of state or a phase change is going to happen here again. So that even when I apply heat to the liquid, some of those liquid that had acquired enough energy changes to gas, leaving behind some liquid. So at this point, we say liquid and gas are at equilibrium. That's it goes into a phase change, and the temperature at which this happens is the boiling point temperature. You can see it is constant, such that if I continue to apply heat to the liquid at this point, it doesn't show or result in an increase in temperature, but rather this heat is trying to free the liquid particles so that we can have gas. At point E, everything becomes gas, and at for E and F, what we have here is steam and gas. You must have noticed something about the curve here. Notice here the melting point temperature is definite, and notice here the boiling point temperature is definite. These are the criteria for purity of substance. When we say criteria or conditions for purity of substances. Talking about criteria for purity of substances, the first one is a sharp or definite or you say precise melting point, to a sharp or definite or precise boiling point. Pure substances dey melt over narrow temperature, or sharp, precise. But for impure substances, dey melt over temperature range, as you see in the diagram displaying on your screen. You have a graph for impure substance where one of the uh, plottings there shows that pure iron melt at 1500. The other plotting shows that the iron is impure and therefore melt over a temperature range. You understand? At that point, imagine, okay, let me have my curve this way. When melting point temperature here is definitely telling me this is a pure substance. Okay, imagine this. Let's say this is solid, and then I have this, and then I have this. So, and I'm telling you that this is liquid, this is solid. So I can't pinpoint in between this solid, and I can't pinpoint which of this temperature is going to be my melting point. I cannot. So telling me that this must be a mixture and not a pure substance. That is why it is melting over a temperature range. So when the melting point or the boiling point of a substance is not precise, is not sharp, is not definite, that tells you that that substance is a mixture, or you say it is chemically not pure. Other criteria for purity of a substance is a definite or sharp refractive index, which is consistent with the standard refractive index of the pure substance. Also, we can use density, which in this case must be consistent, with the pure substance. So these are the four criteria for purity, but emphasis on the first two. When a substance is pure, the melting point temperature and the boiling point temperature must be precise. Okay, let's answer one or two UTME questions that to buttress, to support what we've just explained here. UTME 1994 question 2. It says a pure solid usually melts A over a wide range of temperature. No, it is an impure solid that melts over a wide range of temperature. B, over a narrow range of temperature. C, at a lower temperature than the impure one. D, at the same temperature as the impure one. It is over a narrow range of temperature. You can see that's what I'm saying here. The temperature must be very precise, definite, or at worst narrow. That answers that. Of course, let's quickly explain cooling curve and come back to solving one or two question. Okay, talking about our cooling curve, it is just like the reverse of our heat curve. In this case, we have PQ, talking about a gas in this case. So what happens is that between P and Q, the material here exists as a gas, but from point Q, condensation starts, whereby gases lose, there is a drop in the temperature of the gases, and then the gases suddenly begins to change to liquid. But all of the gases do not change to liquid all at once. Those particles of gases that had lost enough heat energy changes to liquid, while those gas with still appreciable energy continues to remain a gas, so that at point Q and R we say gas and liquid are at equilibrium, and the temperature at that time is like your boiling point, or we call it condensation point. But at point R, look at it, it was gas here, then we have gas plus liquid. But if the temperature continues to fall, if the temperature continues to drop, then at point R, all condensation is complete and all of the material here becomes a liquid. You can see from R to S, it is what? Liquid. And then at point S, if the temperature continues to drop, we say the liquid starts to freeze at point S here. The liquid starts to freeze. If this continues, liquid and solid, of course, when you put like something like your water, your liquid in a refrigerator, all of the liquid does not suddenly become solid at once. Some of the the liquid will become solid while some remain as liquid. So at S and T, between S and T, we say liquid and solid are at equilibrium, and the temperature at which the liquid suddenly begins to change to solid is the freezing point, still as well the melting point temperature. At point T, freezing is complete, and so that at T and U, it exists as solid. That is that about cooling curve. You can see the way your cooling curve goes. You can see the way your heat curve goes. So and of course, I told you you can use your heat curve uh, to derive the criteria for purity of a substance, two of which, and of course the most important, is talking about the sharp or definite or precise melting point, and also a precise boiling point. So that ends that. Do not forget, subscribe, share with your peers.